Whenever you receive something in an instrument case, you know it's probably not going to be cheap. And that is certainly the case here. Inside this instrument case, I've got a UNI-T UT-ISOT wideband injection transformer along with a couple of cables, and it currently retails for just over $300. Thanks UNI-T for sending this in. And in this video, we'll do some experiments with it. So you may be wondering, what is an injection transformer? What's the use of it, and why is it so expensive? An injection transformer, as the name suggests, is used to inject a small signal into an electronic circuit. Now, you may ask, why do you need a transformer? Why can't you just inject the signal directly into the circuit? Well, I guess in some cases you might be able to do that. For example, if the injection point happens to be ground referenced, then you could inject the signal via a blocking capacitor. But most of the cases, you will need a transformer to isolate the signal generator from the circuit under test. An isolation transformer is typically used for loop and phase gain measurements with power supplies. These measurements would be able to determine the phase and gain margin of the control loop, and therefore infer the stability of the feedback. And this is typically done by sweeping through a range of frequencies and use the Bode plot for frequency response analysis. And of course, in this video, I will measure the loop response of a power supply in a little bit. So why is it so expensive? Well, one of the main reasons is that this is a highly specialized product. And there is just not enough volume to offset R&D and production tooling cost. Inside, it is really just a transformer, most likely a toroidal one. Depending on the core used, the material cost could be higher than your typical one. Of course, the winding and spacing are all going to be very carefully designed. I think we should open it up and take a look. Alright, I just removed all the screws. But before I open it up, I want to point out a few things. You can see that the case is actually very carefully designed. The input side BNC ground is connected to the case, but on the output side, the BNC is mounted on an insulated board. This single point of ground avoids ground loops. Ground loops could introduce additional noise and impact the measurement accuracy. Anyway, let's open it up. Well, as you can see, somewhat as we expected, we have a transformer inside. Of course, the transformer is glued down and you have the celestic all over. Obviously, I won't be taking the core out. But you can actually see, if I could just zoom in a little bit more, you can probably see that windings are spaced very meticulously. So yeah, that's what you pay for a wideband injection transformer. You are not just paying for the material itself, you are paying for the design, the manufacturing, and the testing that is involved. Now, technically speaking, you could use any transformer, not even 1-to-1 ratio, for signal injection. But of course, unless you characterize the bandwidth yourself, the results you get would probably be meaningless. And on top of that, your typical transformers have pretty limited bandwidth. And by the way, here is a test report of the transformer. And as you can see, the results across the entire frequency range between 2 Hz and 2 MHz is only plus minus 3 decibels, which is quite impressive. Anyway, just to demonstrate how flat the phase and amplitude is across the specified frequency range, let's actually take a look at the Bode plot. To do that, I'm going to use the built-in Bode plot function of the UNI-T MSO3054X. Basically, any frequency response analyzer can do the job. You might be able to do this with a VNA, but the transformer is probably not 50 ohm terminated, so the results might not be as accurate due to reflection. So here is our setup. It might look a little bit messy, but it's actually quite simple. You can see here, we have the signal generator coming out, and I'm using this BNC to banana cables so we can actually tap in to the input. So the input is connected to channel 1, and the output is connected to channel 2. Now let's take a look at the setup on the Bode plot. Here we start at 100 Hz. Unfortunately, this MSO3054X, the lowest starting frequency is at 100 Hz. Although the transformer can handle all the way down to 2 Hz, so unfortunately we're not able to measure that low. So let's start with 100 Hz, and the stop frequency you can see here is 2 MHz, and we're taking 50 points. That should be plenty for us. So let's give it a go. Okay, I'm going to start a plot. And you can probably see how flat the response curves are. Just to remind you, the red one is for the phase, and you can see that we roughly have a -7 degrees phase shift. The blue curve, that's the amplitude response. You can see that essentially it's 0 dB, it's very flat. We only have a minor bump towards the end. Now we have verified the performance of the injection transformer. Let's actually take a look at the real-world use case. So in the next experiment, we're going to measure the gain margin and phase margin of a power supply. And this is done using the injection transformer to inject a small signal into the feedback loop and measure the crossover frequency, and then derive the phase margin and the gain margin. These measurements are important in determining the stability of the power supply under specific working conditions. Anyway, the power supply circuit we're going to use today is this DC to DC converter board based on LM2596. This board is fairly inexpensive and you can find it everywhere. I will leave a couple links in the video description below if you're interested in getting a feel for your projects. The schematics of this DC to DC converter is very simple, as you can see on the screen here. Now the component values might be slightly different, but everything in the schematics pretty much what we have here on this board. R2 in the schematic is an adjustable resistor, which is this potentiometer on this board. And by adjusting the value of R2, the output voltage can be adjusted based on the formula printed on the screen here, and the reference voltage is roughly around 1.2 volts. So the feedback loop is through the voltage divider resistor R2, as you can see here. To inject the signal into the feedback loop and measure the loop gain, I added a small resistor R3. This is typically 10 to 15 ohms. It's small enough so it doesn't impact the overall operation of the circuit, and the signal would be injected between R2 and R3. Also, the injection point needs to be chosen such that looking into the loop, the resistance is much higher than looking away from the loop. R2 in this case is several hundred ohms, which is much larger than the 10 ohm resistor I used for R3. Signal is then injected across R3. Before I show you the actual experiment setup, let me actually walk you through the setup on paper first. Alright, I just quickly sketched in what the setup looks like. I could have used software to make it prettier, but anyway, this is quick and dirty. So you can see this is the circuit we were talking about earlier, and here are the resistors we mentioned. These R3, R2, and R1, they form the voltage divider. And here is the setup. Here is our oscilloscope. You can see that. The signal generator essentially outputs signal, and you can see that it goes through this injection transformer. And then the signal gets injected across R3. Remember, R3 is only 10 ohms, so this is very small. And then we measure the input, which is channel 1. As I mentioned earlier, it's very important to set the input and output correctly. The reason channel 1 is tapping into the bottom of R3 is between the R3 and R2 is because this is actually looking into the loop. You can see here, looking into the loop is through R2. And that resistor R2 is much higher than resistor R3, which is coming out from the loop. And R3, you can see that that's coming out from the loop. So that's the output. Of course, channel 1 and channel 2 would be grounded at the bottom of R1, which is the common ground of the circuitry here. I just modified the DC to DC converter a little bit. I removed the potentiometer and put 2 resistors in. So these 2 resistors are the R2 and R3 in the diagram shown earlier. And I will measure these just in a moment. But given these resistor values, the output would be around 3.8 volts. So the actual output value is not that important. This happened to be a reasonable value based on the components I have. I also put some load at the output to simulate a typical operating condition. These are 2 10 ohm resistors, so the output is actually 5 ohms. So given the output voltage, which is roughly 3.8 volts, the current draw is right around 0.8 amps. That's a reasonable current for this DC to DC converter. And let me just briefly show you the values on the board here. And you can probably see, by the way, I didn't mention that earlier, this tiny resistor here, that's actually the R1. So that's already soldered in. So let's actually measure that. And you can see R1 is roughly 318 ohms. And now let's measure R2. R2 is roughly 320 ohms. And finally R3. And you can see that's our 10 ohm resistor. So the output, of course, as I mentioned earlier, is 5 ohms roughly. Yep, you can see that. So no issues. Now I'm going to hook up the circuit and we'll be right back. All right, Now, of course, everything looks like a mess. That's just because we have so many wires, but let me walk you through the setup here. So you can see we are powering this DC to DC converter using an external power supply. Currently, the power supply is set as 10 volts input, so that's plenty for driving the output. Now you can see here, this is essentially the output from the injection transformer, and injection transformer, the input is from the signal generator. You can see going into the injection transformer and output, we're connecting to the loop. This is a cross. By the way, this is the center point between R2 and R3. And you can see indeed we're injecting the signal into R3, which is the resistor to the right. And here we have two probes, and the yellow one, of course, is channel 1. The purple one is channel 2. You can see that the channel 1 measurement is between resistor R2 and R3, and the channel 2 measurement, which is the purple one, is at the output. Of course, then we have the ground clipped onto the output resistor. So that's essentially the same setup as what I have shown in the diagram here. Now let's take a look at the Bode plot setup. Here you can see the start frequency is 100 Hz, the same as before. The stop frequency, I set it to 500 kHz instead of 2 MHz. Although the transformer itself can go up to 2 MHz, the operating frequency of the LM2596 is well under 200 kHz. So this frequency range is sufficient to be able to measure all the parameters we're trying to measure. So with this frequency range up to 500 kHz, we should be able to get all the details we need. You notice that actually the setup on the amplitude side is slightly different. Instead of using a fixed amplitude, I changed it to using a variable amplitude. The reason for that is because towards the lower frequency end, the measured curve tends to vary quite a bit, and that's due to the sensitivity. So to compensate that, I actually increased the amplitude output at lower frequencies. You can see here, greater than 10 Hz, between 10 Hz and 100 Hz, we're outputting 100 millivolts, and between 100 Hz and 1 kHz, we're also outputting 100 millivolts, and above that, we're outputting 20 millivolts. So that should be able to compensate the lack of sensitivity towards the lower frequency end. And I also increased the scan points to 200. I actually probably will do 250. Actually, let's do that. Let's do 250. And the reason is because we're covering a very wide frequency range, and I want to make sure we capture as much detail as possible. The downside of this, of course, is going to increase the plot duration, as the Bode plot has to scan through each frequency point, and this is going to actually take some time. Before I start the Bode plot, I do want to mention that the Bode plot function on this MSO3054X is somewhat limited. After the plot is done, you can't really interact with the result graph. But as I mentioned earlier, the phase margin is measured at a frequency where the gain is at 0 dB, which is the crossover frequency. I'll probably have to put a number on the screen afterwards, as we actually had more precise reading while the Bode plot was running, because the range was narrower. After the Bode plot is done, you will see that the curves would be pretty close together, and you can't get readings that accurately on the graph anymore. Because we have 250 scanning points, it will be relatively slow, so I'm going to speed up the video so that you don't have to wait. And that's a beautiful Bode plot, and let's actually do some analysis based on what we measured here. So now let's take a look at the plot. The sine trace, that's our gain plot across frequency, and you can see here at the lower frequency range, the gain is very high, which is to be expected. Of course, the gain started rolling off as the frequency increases. And at some point, roughly around 20 kHz, you can see here, that crosses the 0. So this is between this point and our phase plot. That's our phase margin. On this diagram, you can see that's roughly 60 degrees. Similarly, we can see the gain margin when the phase shift crosses 0 degrees. Now, if you read other literature, the textbook version of the gain margin is actually referenced against the phase shift of minus 180 degrees instead of 0. And the reason we're using 0 here instead of minus 180 is because we are measuring along the feedback loop path, and there is an additional 180 phase shift. I'm not going to dive into the details on this, but that's why we're measuring against 0 degrees instead of minus 180. So you can see on the graph here, now the graph here is getting a little bit crazy towards the higher frequency end. That's because the feedback loop is getting unstable. But right around here, you can see the phase crosses 0 degrees, and that's actually the gain margin. So from the diagram here, you can see it's roughly around minus 15, 16 decibels. So hopefully with this experiment, you get an idea of how an injection transformer is actually used. Of course, in real-world measurements, you would put the power supply under different load conditions. With different input voltages, essentially change all possible parameters and see what is the minimum phase and gain margin. And that ultimately determines the worst-case scenario. And that's pretty much what I wanted to cover in this episode. I hope you enjoyed this video and learned something new. If you're interested in this injection transformer, you can check out UNI-T's website, linked in the video description below. If you liked the video, please remember to give it a big thumbs up, and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.